Hi. Hello, everyone. Thank you for joining this session. My name is Hiroyuki Ishii. I'm working at Panasonic and also being a member of AGL project. Today, I will talk about debugging tools and techniques for virtualized automotive systems. And sorry. And actually, this is a slightly simplified version of my previous talk at EOSS 2 weeks ago. So if you find any unclearness or lack of information due to my potential oversimplification, please feel free to ask me anything, even after this session. Okay, so let's hear the agenda for today's talk. First, I will provide a brief introduction, and next, we'll quickly explore various debugging tools useful for the virtualized systems, and then we'll deep dive into a practical example, where we'll analyze the vHostNet, which is a typical component in virtualized systems. And finally, I'll wrap up this talk. Okay, now let's get started with the introduction. And let me introduce myself again. My name is Hiroyuki Ishii. I have been working at Panasonic Automotive Systems for more than 15 years and have experience in Linux-based software development for IVI and CDC products. And my primary areas of expertise are Linux kernel, performance engineering, virtualization, and cloud-native solutions in recent. And in 2021, I joined the AGL project, where I serve on the steering committee and system architect, and also contributing in various roles, such as virtualization expert. So let's take a look at some background trends in automotive software. In recent years, there are various requirements arising related to software-defined vehicles, such as high-performance computing, hardware scalability, workload distribution, mixed criticality, and many more. And in response to these needs, there has been a growing demand and initiatives for virtualization as key technology for these requirements. And as many speakers mentioned during this event, AJ has been actively worked on the various virtualization activities to address these needs. And one typical example for that would be the virtual machine-based demo integration using KVM. However, there are big challenges associated with the complexity of the virtualized systems. These include complex interaction between the host and guest, and increased system footprint or complicated integration, and limited capabilities and visibility within the guest environments. And as a result, debugging or performance engineering on such systems become increasingly difficult. And complications arise in the understanding the overall system behavior. And to address these challenges, there is a growing need for specialized tools and techniques for the virtualized systems. All right, so let's proceed to the next section. In this section, we'll review various tools available for virtualized systems, including perf, trace command, BCC, flame graph, and debug-infd. So the first tool is perf, which is a powerful profiling and tracing tool for Linux systems. Perf acts as a front end for various tracing technologies in Linux, such as perf events, ftrace, and kprops. And it's developed within the Linux kernel source tree, which ensures it is stable and reliable at certain level. However, this also means that perf has a strong dependency on the kernel version, which may impact its compatibility across systems. Additionally, some hardware events supported by perf are platform dependent, which may limit its usability in certain cases, for example, on ARM platform. The next tool is trace command, which is a front-end tool for ftrace developed by the Steven Rosted. And trace command provides features somehow similar to perf, but with a simpler and more user-friendly interface, in my opinion. And one notable thing is that some recent updates in trace command is designed for embedded and virtualized use cases, including trace command agent or trace command listen. And in particular, trace command agent, which allows us to trace both host and guest at the same time, will be pretty useful for these use cases. But unfortunately, it's not working on the ARM platform as of now. And next is BCC, which is a BPF-based tracing tool designed for the performance analysis and debugging. BCC offers a rich set of features, including Python support, various practical example scripts, and the ability to simplify the creation of custom tools built upon it. However, there are also some drawbacks to using BCC, which includes its relatively large dependency, in particular on LLVM and Python, which may not be ideal for some embedded use cases. Additionally, BCC also has a limited support for the ARM platform, so we cannot use some of good scripts in BCC, such as KVM exit on ARM as of now. And also, I will apologize that I have omitted BCC examples from today's talk, but I think it's still powerful and usable tool. So if you're interested, please feel free to contact me later. And next is FrameGraph or FrameGraph.pl, which is a visualization tool for performance data samples. This tool helps you understanding the workload overview and identifying bottlenecks within the system, as shown in this picture. And the last tool is Debug-info.de, which is a bit different types of tool than the other I mentioned. It's a host daemon for handling and managing debug info files. Debug-info.de is developed as a part of LFUT's project, and it's compatible with numerous popular debugging tools, including GDB, perf, trace command, BCC, and many more. Debug-info.de is especially beneficial for embedded systems, as it allows for offloading debug info files from the target system, which solves storage limitations in embedded use case. And additionally, Debug-info.de resolves path conflicts on debug info files within virtualized environments. And additional advantage is its seamless integration into the yoked build system, which enables you to utilize it with just a single command. All right, so let's deep dive into a practical example using these tools. The goal of this section is to gain knowledge of debugging tools, usage and techniques in a virtualized environment through practical examples. And as example, we'll investigate the behavior of vHostNet, which is an acceleration for standard Virtual, but by comparing it to the standard one. And we'll explore how and why it can improve performance as well as any potential side effects that could exist. The detailed steps for setting up tools can be found at the end of this slide. So if you're interested, please download this slide from skate.com. Okay, now let's quickly look at the difference between standard Virtual and vHostNet. The key difference lies in the implementation of VirtualNet device emulation, where when vHostNet is enabled, the emulation shifts from the QEMU user space to the dedicated vHostNet kernel thread. So this change can result in improved performance and reduced overhead. But I will not go into too much detail here, as we'll analyze it by the tools later. Okay, so before we dive into the analysis, let's quickly go over the preconditions. First, I'm using the AGL-KVM demo platform image built from the AGL-UCB master branch as a base image. And I have installed additional tools, including vHostNet support, iPath3, SSH, and various debugging tools into the base image. And my test environment is running on AGL reference hardware, which has Renesas Alka H3 SoC with 8 physical CPU cores. And it hosts a single guest VM using QEMU with SMP set to 4, which means guest VM has 4 virtual CPU cores. And during this analysis, I'm generating network traffic between the host and guest systems using iPath3 to load the network virtualization system. And to ensure the accurate result, I have halted all other workloads prior to the investigation. And I will be comparing metrics and traces between vHostNet and standard Virtual, in other words, with and without that vHostNet by utilizing tools such as perf and trace command and frame graph and so on. So let's begin with a simple bitrate measurement using iPath3. With standard Virtual on left side, the bitrate was 1.66 gigabit per sec. On the other hand, with vHostNet right side, it reached 3.26. And so this shows that vHostNet is about 2 times faster than the standard Virtual.net, which clearly represents the benefits of using vHostNet. Then we'll start some deeper analysis. Here we are observing the number of KVM-related event occurrences using perfstat command. This kind of statics overview is usually a good starting point to understand the system behavior. And one technique here is that we are sending the specific number of packets to ensure the same load is applied to the different systems. So we can see various events from the results, but key observations here are the significant reduction in WFX, which means a standby event for the vCPU cores, and also wake-up events as well. And we can guess that these may have some relation to the performance improvement in vHostNet. Next, let's try to take performance samples across host and guest. For this, we will use a perf kvm record command. And here we are showing some setup tricks for using perf kvm command. So this shows the result of path KVM record in standard virtual environment. As you can see, workloads on both host and guest are visualized in a single screen. I mean, the second and third rows here indicates the host workloads, and the following two rows are guest workloads. For example, the top line of this output shows that a kernel function of the guest kernel named receive buff consumes about 20% of the CPU in the guest system context. And please note that process names starting with a colon like this, represent child threads of the another processes. In this case, all of them are the vCPU threads of the QEMU process. And here we can observe that 2 out of 4 vCPUs are working in these use cases. So from this output, we can analyze high load functions in detail across both host and guest at once. However, this function level of detail can be often be too much. So now let's summarize the previous result using a sort option. This is the result summarized by processes. In this view, you may gain a better understanding than before, and it could make comparing two different results easier. But please be careful as the workloads here also includes idle functions. Therefore, you need to identify the idle functions by grepping and manually exclude them from the result of each processes. The result after exclusion are shown at the bottom. As you can see, the overall CPU consumption has significantly decreased in the vHostNet environment for each of the processes. So this clearly indicates the efficiency of vHostNet. Okay, then let us try to look at function level workloads again using flame graph. The basic usage of flame graph is outlined here. And this is also some tricks for the virtualized environment. And these are the results. I think the font might be too small, but we'll zoom into the important parts later. So flame graph allows you to visualize system-wide stack traces. In other words, the function called hierarchy. The horizontal axis here represents the total duration of the functions across all CPU samples. And the vertical axis is the function stacks. The stacks are displayed from the bottom to top, and with the bottommost element indicating the process name. And this visualization makes it easier to understand the performance bottleneck and its flow of execution all at once. Now let's take a look at each part. First, the guest side, which includes IPAF3 and swapper K-thread, has almost similar workload between standard BART-IO left side and vHostNet right side. As well, IPAF3 on host has quite similar workload. And about the swapper K-thread on the host, the workload appears somewhat similar, but the idle time is slightly longer in the case of vHostNet, and which means the efficiency of vHostNet. And finally, we can observe that the primary difference lies in QEMU and vhost case rate of the host. And here we can also understand that the same function load, which name is target user, appears in different contexts, such as QEMU left side and vhost right side. So this clearly visualizes the shift of network device emulation from QEMU user space to the vhost kernel thread. And additionally, we can identify another important difference here, which is the usage of system calls. In the case of standard byte I/O, as QEMU is a user process, it must utilize system calls, specifically write-v, to invoke kernel functions such as target user. But in contrast, in case of virtualnet, there's no need for system calls because vhostnet is a kernel thread. And this results in the difference of overhead. In the case of standard BAT/IO, we can see that many intermediate functions are being called before reaching target user. This results the loss of CPU time, and as shown by the time difference between the bottommost caller function and the actual load function. So here we can say that QEMU generates significant overhead during network packet transfer, primarily due to use of system calls. All right, so let's move on to the final exercise. Here we will try to trace the interactions between the host side and guest side using trace command record. And this slide outlines the procedures for recording the traces. And here is the result of the standard result for the standard BAT/IO environment. I know that may seem too complicated, but let me explain it step by step. So first, we need to understand that there are two physical CPU cores at work. One for the guest vCPU and the other for QEMU's main thread, which is also known as IO thread. Then let's begin examining the sequence. The starting point is this MMIO event, which is initiated by the guest vCPU, and this prompts the host to transfer the next network packets. Then the QEMU IO thread awakens by scheduler, and afterward, the guest vCPU enters to the sleep state using the WFX event, which we observed previously. And it then awaits for the next event, which is the completion of the network transfer. And next, the QEMU IO thread invokes target user function, which indicates the packet has been transferred to the physical network interface. Then QEMU handles the IRQ event to notify the guest about the completion of network transfer. And then the guest vCPU woken up again from the sleep state. And finally, the next MMIO event is invoked, which means the end of the sync sequence. So let's evaluate the durations here. The total duration for one sequence is in standard BAT/IO environment is about 400 microseconds. And we can infer that the root cause of this duration is likely due to the vCPUs sleep and wake up, as well as the use of system calls we found previously. And in case of vHostNet, we can clearly see that the sequence becomes shorter. Additionally, we can identify two notable differences in the sequence. The one, there is the vhost case rate walk-in, and two, vCPU doesn't invoke WFX. And the total duration for the one sequence in vHostNet is less than 200 microseconds. So in conclusion, we have observed over 2 times time efficiency in vHostNet from the sequence trace. And these results are highly consistent with the bitrate measurement using IPAF3. And essential reasons for this improvement would likely include the removal of QEMU user space, which utilizes system calls from the critical path, and also the minimization of vCPU sleep and wake up occurrences. Okay, so let me wrap up this talk. In summary, during this presentation, we have confirmed the value of vHostNet by the behavior analysis, and also demonstrated how differences can be observed from both tracing and performance sampling perspectives, using specialized tools for virtualized environments. And as a result, vHostNet is twice as fast as the standard VirtualNet, with no significant side effects observed, especially in terms of CPU utilization. Additionally, various methodologies and tools are covered in this talk. I believe they can be applied to a wide range of development scenarios for virtualized systems. These including analyzing performance improvements or regressions, and as well as debugging and walking through the virtualized systems. So next steps, I will contribute materials to AGL, which likely includes some debugging tools and maybe vHostNet support. And I will also explore some additional tools, such as porting a trace command agent to AX64, or maybe try to develop custom tools using BCC. And also, I will investigate on containerized or environment or cloud environments. So that's all of today's talk. Thank you. Any questions?
Thank you for interesting presentation about the debugging tools and the practical profiling. I've never used the debug FSD and debug info D. I want to ask about the debug info D. You mentioned that you briefly explained at page 17 about the debug info D.
Yeah.
Thank you. I'm talking, it is debug, the tool can be offloading debug info from the target files. I don't understand what do you mean the offloading. Could you explain that?
Yeah. That could be the mischoice of my words. So it means that you don't have to install the debug info files to the target file system. So debug info files are hosted from the host PC, development PC by network.
So the debugging for the is run on the host system.
Yeah.
That makes sense. Thanks.
Yeah, as shown here.
Sorry.
Yeah.
I overlooked that.
Yeah.
Thank you for your answering.
Thank you. Any other questions? Nothing? All right. Thank you, everyone.